Prove that the relation S on the set of real numbers are defined by the ordered pair a comma b belonging to the relation S if and only if a squared plus b squared equals to 1 is not an equivalence relation on the set of real numbers. Okay, let us begin. So here we are given a relation S on R. Relation S on R, this simply means that we have the relation S being a subset of the set of real numbers R. We take its Cartesian product with itself. And that's what it means when we say S on R, the relation S on R. And the relation is defined as S will be a set of ordered pairs A comma B, such that we need to give a relationship between the elements A and B. That's given by A squared plus B squared equals to 1, where A and B, these are real numbers. Fine. So this is our relation S. We have to show that this is not an equivalence relation on R. Now, what does it mean when we say a given relation is an equivalence relation? So there are three things that we need to check. We need to show that the relation S, if it is reflexive, if it is symmetric, and also if it is transitive, then the given relation automatically becomes an equivalence relation. Fine. So for any relation R on the set A, R is going to be reflexive if and only if we have the ordered pair A comma A belonging to the relation R for all values of A belonging to the set A. R is going to be symmetric if the ordered pair A comma B belongs to the relation R, if that implies that B comma A also belongs to that same relation R for all A and B belonging to the set A. And then finally, R is going to be transitive if the ordered pair A comma B belongs to the relation R and B comma C belongs to the relation R, would imply that the ordered pair A comma C belongs to the relation R for all A, B and C belonging to the set A. Okay, fine. Now, here before continuing, we have to be very careful how we choose the two ordered pairs for the relation R to check whether if R is transitive or not. So here you can see that the second element of the first ordered pair, which is B in our case, is going to be the same as the first element of the second ordered pair B comma C. Only then we can say that A comma C, the new ordered pair, that also belongs to the relation R. Now, only when all of these are satisfied, that means R is reflexive, R is symmetric and R is transitive, then only we can say that the given relation is an equivalence relation. If only one of them also does not satisfy, or you can say fail to satisfy, then the given relation will automatically become not an equivalence relation. That is what is going to happen in this case. So let's start by first checking out reflexivity. So for this, we are going to consider an arbitrary element A that belongs to the set of real numbers R, such that if we consider the ordered pair A comma A, that's very important, for any element, arbitrary element that's been picked up from the set of real numbers R, the ordered pair A comma A must belong to the relation R. Now, what does it mean when we say A comma A belongs to the relation S? Now, what does it mean when we say that the ordered pair A comma A belongs to the relation S? This simply means that this is going to give us the relationship between the two elements as A squared plus A squared equals to 1. Now, A squared plus A squared equals to 1. When we solve for this, we get A equals to plus or minus 1 over square root of 2. Now, that is the problem here. The problem here that we are getting a very specific value for A. So, A can take only the value 1 over square root of 2. Or we can take a positive and negative value. Only in that particular case, this equation is going to be true. That means the relationship between A and B, the first element and the second element of the ordered pair, is going to be such that only when A equals to 1 over square root of 2, then this equation holds true. Any other value of A that we take, it's not going to be true. We can verify that if we take A to be equals to 3 over 4, then definitely A squared plus A squared cannot be equals to 1. But our property states that R is going to be reflexive for all A belonging to the set A. That means any real number that we pick up, this equation must always hold true. Since it is a very specific case, so here we can immediately say that our relation S is not reflexive. So here we have shown that our given relation S is not reflexive. So of course, in one of the properties failing, so we can stop here and say that yes, our given relation S is not an equivalence relation on R. So however, what we'll do, since we are checking for equivalence. Let's check for the other two properties as well. Let's check whether if R is symmetric or transitive or not. Okay, of course we could have stopped here and say that yes, S is not an equivalence relation or R. Okay, now let's check for symmetry. So let us consider two elements a comma b belonging to the set of real numbers such that if we choose the ordered pair a comma b belonging to the relation S, this would simply mean, according to the definition, that a squared plus b squared equals to 1. Now, a squared plus b squared equals to 1. We can also rewrite it as b squared plus a squared equals to 1, since addition is commutative. Now, the reason why we're writing b squared plus a squared equals to 1, this simply means that the ordered pair b comma a also belongs to the relation S. Fine. Now this, we can write this because our definition, that means our relation S is defined as the set of ordered pairs a comma b such that a squared plus b squared equals to 1. And if we interchange the position of these elements, then we'll get the ordered pair b comma a. So that's going to give us b squared plus a squared equals to 1. And that's what we are getting, b squared plus a squared equals to 1. So this is telling us that our given relation, so here in this case, S is symmetric. S is a symmetric relation. Okay, right. Then let's go to the third one. So in the third one, we have to check for transitivity. So here we're going to consider two ordered pairs a comma b and b comma c. So let a comma b belongs to the relation S and b comma c also belongs to the relation S. Now a comma c belonging to the relation S means a squared plus b squared equals to 1. That's how we relate a and b, the two elements inside the parenthesis. And then b comma c, that's going to give us b squared plus c squared equals to 1. Fine. Next, what we'll do, we're going to isolate b squared from here. So b squared will be equals to 1 minus a squared, and when we substitute b squared with 1 minus a squared in the second equation, we get 1 minus a squared plus c squared equals to 1. So solving for this, we get a squared minus c squared equals to 0, but that simply means that the ordered pair a comma c does not belong to the relation S. Why? So here transitivity means that if a comma b belongs to S and b comma c belongs to S, we should get that the ordered pair a comma c also belongs to the relation S. Now the ordered pair a comma c belonging to relation S translates to saying we have a squared plus c squared equals to 1. However, we're getting a completely different equation, a squared minus c squared equals to 0. So that means that the ordered pair a comma c cannot belong to the relation S. So we can say, so our relation S is not transitive in nature. This is not a transitive relation. Now, since it is not a transitive relation, it's not a reflexive relation, and it's only symmetric, so we can immediately say, hence our relation S, hence S is not an equivalence relation. Hence it is not an equivalence relation on the set of real numbers R. Hence proved.